Yeah, we're gonna talk about the piezoelectricity stuff. This was a paper me and my buddies got out in September. It's pretty weird stuff, but it's like fun stuff. I hope you think it's fun. I do. Um, so we're gonna talk about gold deposits, in particular organic gold deposits, and typical, first slides about why we care. Unfortunately, critical metals isn't on this slide, but please give me your attention anyway. So yeah, ore deposits, you guys know what these are. So like ludicrously enriched elements in comparison to the crust. So one thing gold does, which is a bit weird, is it stands out as being one of the highest degrees of enrichment. So there's that little like size scale on the bottom. For example, to make a copper or other base metal deposit, you might need like 200 or 300 times what the crust has. Whereas gold requires, 10 to the 3 or 10 to the 4 to make a gold deposit. And that's to make a typical mineable gold deposit. And then when you look at like really crazy gold nuggets that you see photos of or that you might have seen yourself, I don't know what that enrichment factor would be if you want to compare how much gold is in, let's say a hand sample that's full of gold in comparison to the crust. I'd assume it just goes on to almost infinity. So there's a couple examples I had here that Steve Kerner gave me. They're not even the most fantastic ones, but just like good images of them. But what kind of enrichment factor this staying, in comparison to the crust, something probably a little bit out of control. I'm going to do the risky business of trying to show you a video in a PowerPoint. This is always like a bit of Russian roulette. Hey, look at this. It's not working. Well done. Is it because I have a laser pointer?
Yeah.
Oh, look, I'm learning.
Give me a moment, guys. Technical thing.
Incredible. Cannot play media. Yes. Codec unavailable. Awesome. No, there's no audio, but it's okay. It's just a tomography video. I just wanted to show it off because I've been doing a lot of tomography. I could be like, hey, look at how nice it looks, but you guys don't get to see that. You don't get to see how nice it looks.
I don't know if I do.
It's okay. It's fine.
It's unavailable.
Yeah, look, that's what happens when you put them in the PowerPoints. But it's okay. I could show you videos later if you guys like on my computer. The point is, we're just going to show you a lot of gold in one sample. So a lot of these really large gold nuggets that I tend to talk about, or people tend to talk about, they come from organic gold type deposits. Again, I'm sure that a lot of you guys know probably more about this than even I do, but in case you don't, we'll talk about sort of the basics of them. So the source is usually metamorphic fluids, right? So you have like a low salinity, water-rich, CO2-rich fluid source that comes from metamorphosing a pile of rocks and around the amphibole facies. So the gold usually comes from the prograde metamorphism of sulfides like iron and peritite, for example, will like liberate some sulfur and also give you some metals that would trace metals in the pyrite. And then you can make a lot of water from dehydration of more silicate mineral silicates, chloride into amphibole or even biotite, depending on how prograde you get. So the depths, mesothermal, mid-crustal block, just generic sort of mid-crustal conditions. And the temperatures, again, we could say 300 plus or minus 50, but it's, you can get them a lot cooler than that in their form. So for transport, it's gold as a sulfur complex. That's great. pH is near neutral. And then for deposition, these things aren't normally on big first order regional structures. They like to be on sort of higher order things, splay faults like that. And the mechanisms that we think make gold occur, I mean, there's stuff like wall rock sulfidation, of course. So if you had reaction of an iron-rich rock, you could, let's say, turn magnetite into pyrite, let gold come out. It doesn't have a sulfur ligand come. Things like reduced carbon are good for just reducing gold out of solution. Rapid pressure decreases, maybe, especially if there's a vapor or phase separation can help that. And then the hosts are often greenstone belts in Archean and slate belts in the Phanerozoic. And I like showing this thing. But what you're looking at is pretty much fossilized earthquake events. So a quartz vein there's some laminations in it, which you can say are sort of analogous to earthquake events. There'd be more earthquake events than just the 3 laminations you see. There'd be many more that are in the quartz. But what you can see is multiple fluid events or earthquake events, and then gold associated with those. So when you look at it on a little depth scale, you can think of the source of gold here. So metamorphic source region, so something around amphibole facies for the dehydration and making of a fluid. And then you have stress transfer, you have earthquake and failure, and then you can bring the fluid up to more shallow levels of the crust where we find them deposited. So this is great, but I mean, when it comes to these natural fluids or natural gold forming fluids that we can measure and we can see, or even ones that have been modeled by people like Willie Jones, normally the gold's less than 1 ppm. I mean, even something like 10 ppb is probably an honest representation of how much gold's in a fluid. So gold nanoparticles are offered as a sort of a solubility solution. Whether you think they're transported as nanoparticles from the source or not is entirely up to you. I don't personally think that's true, but science is fun for these reasons. But we still need an accumulation mechanism regardless, right? So if you like nanoparticles, it's fine, but now we have to stick them together. We have to build a nugget out of them still. So the textures and chemistry that we see at deposits, they can support things like, wall rock interactions. So you could see alteration mineralogy telling you that fluid compositions have changed. You could see things like, let's say bladed calcite or something telling you there's boiling, there's phase separation. Then we could start talking about mechanisms that make gold form. But it's not always the case. Sometimes you can find gold sort of floating in the center of a boring vein. So let's say you have some 2-meter bulk quartz vein, and then there's just a big chunk in the middle, and you're like, oh, okay, now it's getting a little bit more difficult to blame a mechanism for this. But one thing that's common is, of course, quartz veins, right? But they're one of the most inert minerals once it's formed. And it's also the only abundant piezoelectric mineral. There is, there's other sort of non-central symmetric minerals that can be piezoelectric. Tourmaline is probably the second most abundant one, especially for association with gold. But quartz is by far the most abundant piezoelectric mineral that we have. So what does that mean? What is that? So it's generating electric charge in response to mechanical stress. So this is barbecue lighters, right? This is the click, click, click. It's a hammer that hits a piezoelectric crystal, and then it'll spark to a nearby metal prong, and then it ignites whatever fuel is going by. It's a reversible effect. So it also means if you put electricity into a piezoelectric crystal, it actually mechanically strains, it'll wiggle, and that's what a quartz watch is. So you put a battery in your watch and it puts a voltage across, and quartz wiggles whatever 6,000 times a second, and that's how you keep track of time. So it is directly proportional to the amount of strain you put in. So more strain means more potential. And yeah, modern uses, yeah, lighters, microphones, watches, etc. I just have a little back of the envelope calculation. So if you were, super careful and applied whatever 2 kilonewtons of stress, you can make a tremendous amount of voltage. But the reason that this works is because you offset these charge balances that are in the structure. So you have, let's say 3 positive silica cations and 3 oxygens that are negative. And when you distort that, you end up polarizing across the crystal. So the voltage goes across that chemistry. So there has been sort of a little bit of research in this kind of thing in the past. Probably the most prominent thing is seismo-electrokinetic exploration, which was popular with the Russians in the 70s, which is basically like you're doing an IP survey, but you bring out like a shaker truck to shake the ground for you. And what they could do is detect quartz veins at depth. One of the most common questions I've got since this paper comes out is, how do we find gold with this? Then I always go, you can't. And then people get really, really disappointed. But one thing that people have done, and was not invented by me, is this thing, this seismo electrokinetic exploration. So you can detect quartz. You can't detect if there's gold in that quartz or not, but you can find veins if you're looking for those things. The other thing that's been blamed on piezoelectricity is something called earthquake lighting. This is still debated. This is not settled, but something that does occur throughout a large magnitude of different earthquake sizes. So everywhere from, sort of 2s and 3s upwards to magnitudes 7, 8s, is this thing. So it's like almost like a plasma that appears right before and sometimes during earthquake events. So when you have the largest amount of stress transfer before failure, it ionizes the lower atmosphere. And some people blame piezoelectricity for this. So by generating a large voltage, you can just ionize the lower part of the atmosphere if it's in a humid place. Again, it's debated, but it was something that when I read about it, I was like, yeah, smoking hot evidence, let's go. And then there was work by Bishop in 1981. So he defined what was called a piezoelectric fabric, which is the same as any metamorphic or structural fabric. What he did was he took a basically unmetamorphosed or non-deformed sandstone, measured the piezoelectricity off it, so hooked up some electricity, smacked it, measured the response, and then he did that for a bunch of varying degrees of myelinites. So then as they got more and more sort of aligned, as the CPO, the crystallographic preferred orientation, got higher, the piezoelectric response was actually bigger. And the idea being that if you have a bunch of random quartz crystals and you strain them, their voltages can cancel each other out partially. Whereas if they're all aligned, you can actually add up their voltages. And I thought this was going to be super important. So I was like, oh, we got crack seal vein textures and stuff like that. And it turns out it actually doesn't really matter that much. It does change, but nothing's really as strong as a single crystal of quartz. because it's the strongest CPO you can have, right? One thing is perfectly aligned with itself. It's the greatest CPO you can have. So we took a couple of samples that had gold in them, quartz vein samples from Fosterville, and then we did neutron diffraction on them and calculated their texture. This is mostly Nick Hunter's stuff. He's a really good quartz scientist. And then we calculated the piezoelectric response, the tensor that we should get out of it. So what we found was you got anywhere from 0.1 volts per meter to a maximum of 0.03, which is not very much. So that's these points down here. So when I said it didn't really matter, that's what I'm kind of talking about. I think the most piezoelectric sample Bishop did in his study lands somewhere about here. And that was from an exceptionally strained myelinite. But what this does tell you is that this phenomenon or this effect is actually just going to be localized on the surface of individual crystals. It's not necessary to have a really strong fabric to generate a big piezoelectric response, because the largest piezoelectric response is generated by a singular crystal. So why do we care? What's the point? This is work that was done by Matt Starr-Burke. This guy is out of Madison, Wisconsin. He's a material physics kind of guy. But he was doing things they're piezocatalytic reactions. So a chemistry reaction that basically uses piezoelectricity as its catalyst, the thing that pushes it forward. So the way that this works is that the conduction band and the valence band of the material can shift. So when you put a potential across it, their energy states actually move. The easiest way to think about this, I think, is think about the classic orbit model that you learn for atoms, like when you're in high school. How you have the outer band that's partially filled, and then the inner band that's totally filled. So that would be the conduction in the valence band, with valence band's the inside one. So for an unstrained piezoelectric material, there's this thing, EV, which is the valence band, and then there's EC, the conduction band, which is partially filled. If you strain a piezoelectric material and you strain it enough, the valence band, which is filled, can have its energy shift higher than the lowest energy state of an atom that's in the surrounding solution. And when that happens, the electron jumps out to lower its energy state. And that's just reduction, but that's how this kind of reaction works. Likewise, on the opposite end, it can do the same. So if you have that your conduction band gets lower than the highest energy state of something hanging out in the fluid, it can donate electron and it can oxidize. So what he did was he was splitting water with this. So his results are up here. He has time running. He had different oscillation frequencies of this was a man-made piezoelectric material. And when he wiggled it, he was measuring how much H2 concentration he could generate. And that was his results there. But that's what kind of got exciting, because if you can do chemistry with piezoelectricity, and quartz is piezoelectric, and we want to make gold reactions happen. That's sort of where this all this thing was kind of leading from. So there was good electrode deposition studies done by it's called the Moeller model, done by Moeller and friends. But they were looking at something called open circuit reactions in different kinds of sulfide minerals. But what he does report and what's useful are these things here, which are the numbers that are the reduction potentials for the different gold ligands. So I have gold tetrachloride here, and then we have the two sulfur complexes. And you can see it takes 1 volt to drop gold tetrachloride, and then about half a volt for hydrogen sulfide, and then bisulfides, 0.1 volts-ish, which is things we're going to talk about again in a moment. So this was the sort of the Moeller model idea. He had N and P type conductors, which we don't have to worry about too much. But the point is that one acts as an anode and one acts as a cathode. So one shoots an electron and one of them takes that. And this is from the talk that I'll do tomorrow. But you can sort of map out arsenic zoning and pyrites and arsenopyrites, and you could see a gold association with them sometimes. In this case, I thought it worked pretty good. So the green zoning here was showing the arsenic zoning, and then we had sort of gold deposition along fractures that were related to where this changed. So I blamed that on the Moeller model, but what that is just an electron transfer to reduce gold through something that isn't strictly like a chemical reaction. It's through an electric reaction instead. So when we put it all together, like, can you strain a quartz vein during an earthquake and have a piezoelectric deposition of gold? That's sort of the question here. So this was what I threw together. This was the theory. So most of this was done during my PhD before I had funding to do this kind of stuff. But the idea is that conduction and valence bands in quartz act as electron reservoirs. So as I explained earlier, like electrons will live here, and then they can sort of jump in and jump out of the valence band and conduction band, depending on how much you strain them and whatever the energy state of the things around them are. The other thing is that if you have a conductor, if you have any kind of metal in your system, let's say on quartz or nearby, you'll instead use something that's called the Fermi level of the metal. The reason why is because the Fermi level exists between the valence and conduction band. It makes things a lot easier because instead of having to shift this thing enough so that the valence band is higher than whatever the energy state of the surrounding solution is, you only need to shift the valence band that much, and it has to, by definition, exist at a higher energy state. So instead of having to shift something that much, you can kind of shift it this much. So it's easier to do. So if you put that with the cyclical nature of earthquakes that we know that makes orogenic gold deposits, the idea was that sort of the elastic rattling that happens will lead to like an oscillation of oxidation reduction fronts on either side of the quartz crystal. So the whole thing wiggles as fluid infiltration's coming through, and you might have bits of reduction or even oxidation going on while that occurs. So the electron donation will occur on one side and it can actually accept on the other. And then if we're going to consider nanoparticles, those things they do change charge. And Evan knows heaps about this stuff, but I think a lot of people report them as being negatively charged. So I would suggest they stick to it when it's a cathodic surface, like a positive surface charge. So how do you do it? You build one of these things. If I showed you actually, now that this thing's published, I can tell you honestly, that's a massage gun I bought from Kmart. I reported as a linear actuator in the paper because I didn't want to be poo-pooed. But you don't need to buy a really fancy widget. You just need something that does the job that you need. So I think I broke 2 of them while doing these experiments, but they're only $80 each. But what I did was I took single crystals of quartz that I bought from like a woo-woo healing shop down the road. And I had natural gold-bearing polycrystalline quartz vein samples from Fosterville. And for some of the single quartz crystals, I coated them in iridium, which makes them conductive. Cut them into that size slab. The reason I did the iridium coating is because, as I explained earlier, if it has a conductive material on it, you only need to shift the valence band, not the conduction band below. So there's been work by Matt Starburk that shows up to about 0.1% strain. That's when a uncoated piezoelectric material will behave the same as a coated one. So by using a conductively coated piezoelectric material, you're sort of mimicking high strains. You're mimicking strains greater than 0.1%, even though you're not straining it that much. So the idea is that you're sort of replicating like a high magnitude earthquake event as opposed to a Kmart massage gun by doing that. So I ended up with 275 kilopascals of pressure and a frequency of 20 hertz, which is good for aftershock earthquakes. So bigger earthquakes tend to have lower frequencies. Aftershocks have kind of higher frequencies. And then for the experiments, I use 75 ppm gold. That is tons. It's way more than what I said is in nature. But the reason why is that we're working with a slab that's fairly large. And if we actually went with, 10 ppb or 1 ppm, I'd still be on the SEM trying to find the result, whether it was there or not. So we went higher for the purpose of detecting it. And we had to use a sodium chloride solution for this. So AuHS and AuHS2, they're not soluble at room temperature. So if you try to use the sulfide solutions for this thing, you're going to get a positive result, whether it's true or not. So you're wasting your time. So I had to use the chloride solution instead. And then for the other round of experiments, I had gold nanoparticles. So they're 2 to 20 nanometers, and they're stabilized by colloidal silica. So both of these solutions are stable. The nanoparticle one's stable for about a week, and then the chlorine one was stable. It's still stable. It sits on my desk. It's fine. And the things we wanted to look at was nucleation. So can we actually start to make gold nuggets form by doing piezoelectricity stuff? And then growth. Can we grow a big nugget, or how do they grow? What do they look like? What happens? So this was the results from the tetrachloride stuff. So I got the naked one there on the left, and I have the iridium coated one here on the right. So again, I'm trying to mimic sort of, high strain on the right and, just uncoated normal there on the left. And these are just kind of what the results look like. So we ended up with nanocrystals on the left-hand side there. So all these sort of hexagonal and trigonal things, which aren't even the crystal class system of gold, which is kind of cool. But that's also sort of one of the pieces of evidence that it's sort of a metastable effect, like you're making a crystal class symmetry that isn't proper for gold. So it's kind of consistent with early stages of here's a big fancy word for you, electric field induced diffusion limited aggregation, which is way too many syllables to say that electricity attracts things. But diffusion limited aggregation is just when elements migrate under some sort of potential. And then this one's our potential electricity. So you have non-bonded particles, they cluster together and they reduce their free energy. But this is how you end up with like weird structures. So like Browning's trees and stuff like that. I know people have reported things like that from epithermal deposits in Nevada and stuff. You get these sort of dendritic trees that form, and it's usually from these weird sort of nanoparticle-ish metastable reactions to reduce free energy. And yeah, I have written on the bottom. I didn't even know that. And then for the nanoparticle solutions, the ones where we started with nanoparticles. Oh yeah, just an interesting thing here. When I was working with these chlorine solvents or solutions, sorry, I couldn't help but make nanoparticles. It happened almost every time. I thought for the first while that I had contamination issue or something. So I reran it a bunch, and almost every time it would happen, and you could see it happen. So I had like a yellow solution, and I'd be deforming it with the linear actuator. And you could see it go from yellow, and then it would go kind of milky white, and then it would go purple. And you could see it happen in a minute and a half. It was really, really cool. What that means is, ask me later. I can't think. So for the nanoparticle stuff, this is what it looked like. So nanoparticles will repel each other if they're similarly charged or if they have something that stabilizes them. So we're using colloidal silica. So we need to do something to overcome an aggregation barrier. We need to make them stick together. So in this case, of course, we're blaming electricity for this to overcome their repulsive forces. And they would actually cluster together pretty good. I like the results here. They're pretty nice. You could just see these bright spots on that image there. Those are individual clusters. So we're growing things that were, a couple of microns across from solutions that started with 2 nanometer, 20 nanometer particles. So usually when people coat things with nanoparticles, they tend to grow crystals instead of having even coating. It's sort of common that that's the result. And this was probably my favorite one of the experiments. So when we had the natural quartz vein that already had gold in it, one thing we had was an extreme bias to deposit gold from solution onto the pre-existing gold grains. So rather than nucleate new gold crystals and new like little grains, we would only grow on the pre-existing gold, which I thought was super cool. And then it's kind of obvious. I mean, quartz is an insulator and gold's a conductor. So if a voltage is running across it, of course, the conductor is going to do more work. So these like kind of cauliflower crusty looking things here, that's all gold that's come from the chlorine solution. And you can see the primary gold grain that was behind it there. And even on this zoomed out one, these are primary gold grains, and there's very little that's sort of being deposited outside of the trace of the existing grain, which I thought was really cool. So in this way, it kind of behaves like a capacitor. So you have the quartz as a capacitor, and then the anodes or the whatever the electrodes are the pre-existing gold. So I think this is our best evidence for trying to explain, localized, discrete occurrence of large gold accumulation. So, I think I said on the next slide, like so very much underlined healthcare. Another thing that happens is you say something and people are like, oh, so everything's piezoelectricity now. It's like, no, not even close. This thing's meant to help, right? So geochemistry is real, structural geology is real. Everything that we know about gold deposits is still real. I'm not saying this replaces it. I just want to be clear with that thing. But I think it helps. I think it helps explain how you can get, a gold from a large volume of fluid into a discrete location, whether it's destabilized by another mechanism, whether this just helps, whether it has to be a remobilization thing. It's all fine. And I think it does help explain that these interconnected networks in these large gold nuggets. So it is rate limited. So quartz is an insulator, but once gold has deposited, it actually you get a sort of an increased return. Now that you have an electrode in your system, it'll actually help grow into a little area. So that's our preferential deposition. It could explain the nucleation growth of large nuggets, as opposed to other systems that can have really high grades but don't form very large nuggets. So if you have systems that are, not earthquake-related gold systems, they can still be really high grade. They just might not make those crazy-looking gold nuggets that you see from orogenic deposits. And that includes things like the really interconnected fracture networks that I'm sure a lot of you guys have seen, where you have a bunch of almost like gold-coated fracture systems within a quartz vein already. Because piezoelectric voltage is coupled with stress, the most amount of voltage you're going to get is during brittle failure. So when the thing actually fractures and breaks, you'll have the most amount of voltage achieved. And then also the thing's instantaneous and it has no visible tracer. So if you have sort of gold floating in a vein and you're like, okay, hold on, I don't see alteration, I don't see boiling, I don't see whatever, this could help rationalize that. It could be a reason for why you see that kind of thing. Quartz or gold sort of floating in quartz without an alternative explanation, And these are other minerals that I've been starting to work on. So these are like, other sulfides that are associated with gold. So I did pyrite, graphite, stibnite, arsenopyrite. There's a chalcopyrite on the top. This stuff isn't published. This stuff I'm still doing now, but they look pretty slick, I think. Yeah. Thanks, guys. Thanks for listening.